In this question here, we're told to solve this equation in order to show that this is true. As always, the first thing you want to do is separate the variables, because that's what allows us to integrate, which is how we actually solve this thing. So, to start off, we bring the dt to this side, and we move n minus 6 times n minus 3 here, which therefore gives us an equation with fully separated variables. What comes next? Well, remember, to solve a differential equation, we have to integrate. And so, wait, there's a problem. Can you see it? The problem here is that we cannot integrate the fraction in this form, which means we can't solve the equation. So then, what do? To get over this hurdle, we have to see this fraction for what it is. Something that can be broken up into partial fractions. But then how do we do this? We start off by saying that 1 over n minus 6 times n minus 3 is equal to a over n minus 6 plus b over n minus 3, which then simplifies down to 1 is equal to a times n minus 3 plus b times n minus 6. Therefore, if m is equal to 3, then 1 is equal to negative 3b, which means that b is equal to negative a third. And if m equals 6, therefore 1 is equal to 3a, which means a is equal to 1/3. And so we get 1/3 times 1 over n minus 6 minus 1 over n minus 3 dm is equal to k dt, which means then that 1 over n minus 6 minus 1 over n minus 3 dm is equal to 3k dt. Fully integrating this now, we get ln n minus 6 minus ln n minus 3 is equal to 3kt plus c. Therefore, ln n minus 6 over n minus 3 is equal to 3kt plus c, which means n minus 6 over n minus 3 is going to equal e to the 3kt plus c. As the a bit simply represents a constant, this can simply be represented by e to the c. Now, this section is something that can really trip you up if you're not paying attention, because it's done in such a way that the puzzle pieces you need to solve the question are hidden in the question. To be specific, when the reaction started tells us that t equals 0 and no compound present tells us that m equals 0. So therefore our first condition is m equals 0 when t equals 0. A slightly more obvious fact is that it tells us that when t is equal to ln 16, m equals 2. So this forms our second condition. Plugging in our first condition, we get a is equal to 2. Meanwhile, plugging in our second condition, that gives us 2 is equal to e to the power of 3k ln 16. So how do we solve from here? Well, remember your ln rules. From here we just say that ln 2 is equal to ln e to the power of 3k ln 16. Now watch out. This part of the question can easily trip you up if you're not paying attention. What does ln 16 break into? Well, 16 is equal to 2 to the power of 4, which means according to our ln rules, we can take the 4 down, giving us 4 ln 2. Seeing as we have ln2 on both sides here, we can then cancel the ln2's on both sides, which gives us k is equal to 1 over 12. So why were we finding k again? Remember our equation. m minus 6 over m minus 3 is equal to 2e to the power 3kt, which we can now use to just plug in k equals 12, which gives m minus 6 over m minus 3 is equal to 2e to the power of 3 times 1 over 12 t. Naturally, this breaks down to m minus 6 over m minus 3 is equal to 2e to the power of a quarter t. And so solving the equation gives us m is equal to 6 minus 6e to the power of a quarter t over 1 minus 2e to the power of a quarter t. Now we've got a bit of a hurdle again. We've got m is equal to 6 minus 6e to the power of a quarter t over 1 minus 2e to the power of a quarter t, but they want m is equal to 6 minus 6e to the power of negative a quarter t over 2 minus e to the power of negative a quarter t. So how do we change forms here? The answer to that question is to multiply by e to the power of negative a quarter t, because that gives us m is equal to 6e to the power of a quarter t minus 6 over e to the power of negative a quarter t minus 2. But we're not done yet. There's still a mismatch here. The solution? Simply take out a negative, which gives us m is equal to negative 6 e to the power of negative a quarter t plus 6 over negative e to the negative a quarter t plus 2, which finally gives us an answer of m is equal to 6 minus 6e to the power of negative a quarter t over 2 minus e to the negative a quarter t. And that's your final answer. Now part C is a really interesting part of the question. To show that 3 grams of the compound can never be produced, let's firstly plug this into the equation and see what we get. Let's let m equal 3 and solve for t here. So therefore we have 3 is equal to 6 minus 6e to the power of negative a quarter t over 2 minus e to the power of negative a quarter t. The question here then is, when does 6 minus 6e to the power of negative a quarter t over 2 minus e to the negative a quarter t equal 3? Well, 6 minus 6e to the power of negative a quarter t over 2 minus e to the negative a quarter t equals 3 when we have the fraction 6 over 3. And so the question becomes, when do we have 6 over 3? We have 6 over 3 when e to the power of negative a quarter t is equal to 0. But I can hear you saying, e to the negative a quarter t can never equal 0. So what do we do? That's a great question. Because even though e to the power of negative a quarter t can't ever equal 0, e to the power of negative a quarter t can tend towards 0. So when does it tend towards 0? E to the power of negative a quarter t tends towards 0 when t tends towards infinity. As a result, we can say that as t tends towards infinity, m tends towards 3. But m never actually reaches 3. And so therefore, in practical terms, m can't ever actually equal 3.